And we talked about, and we've already done it, calculating means and standard deviation. So I'm going to just check that off my list. And we're now going to do two more things. Next thing we're going to deal with is the shape of bell-shaped data, and we're going to use a thing called the empirical rule. I don't like the name empirical rule. I much prefer this weird name, 68, 95, 99.7% rule. I like that name much better. And that's not one of my made up names. I make up names for things. That's actually a real name for a rule. And I like this rule better than the empirical rule. And we're going to show you how to use it to help you draw bell-shaped data, right? That is based on only knowing its standard deviation and its mean. And the third thing, which hopefully we will get to today, we'll definitely get to tomorrow, is we're going to look at what's called the standardized Z-score, which everybody calls the Z-score. They don't stick the word standardized. And we're going to look at how to calculate and how to use them. So we're going to look at how to calculate the Z-score and how to use the Z-score. And that's pretty much what this chapter, this section of the chapter 2 deals with. So, number 2. This thing called the empirical or 68, 95, 99.7 rule. This empirical rule. It's been discovered that when you get data and that it's normally distributed, right? It's got a nice bell shape to it. Right? Imagine that's a histogram. It's easy to draw it like that, all right? That's right, symmetric, bell-shaped, normal, right? Whatever name you want to call. You've got data that looks like that. And if I tell you that the mean is 100, and I also found the standard deviation was 10. So that's one example of this. Suppose I knew the data had that shape and that the mean is 100 and the standard deviation is 10. It's been discovered that there's a very interesting property about this data. First one is pretty obvious. It shouldn't surprise you. Shouldn't the mean, right, the typical number, shouldn't it be bang in the middle where the top of the hill is? Does that make sense? That's where you'd expect the mean of 100 to lie, right? Right in the center. What you might not have realized is this. If you go one standard deviation, which in this case is 10, so if you go 110, then another one which is 120, and then one more, 130, and then you go back one, so that's 90, another standard deviation back is 80, and one more is 70, right? You will make basically the range of values that almost all your data will lie. So in other words, almost every number in your data set will be between 130 and 70. Oh, remember that test about outliers? The mean plus 3 standard deviations gets you to here, and the mean take away 3 standard deviations get to here. Can you see how we know where outliers live? Right, outside of 3 standard deviations away. Well, that's kind of cool, but that's only the beginning of cool. If you take one standard deviation either side of the mean, in this question here, it happens to be between 90 and 110. Oh, by the way, let me tell you the story. This is actually IQs. Do you know if you take an IQ test and the average Americans get is about 100 and that the standard deviation is about 10? Right? One standard deviation either side of the mean, 68% of all the data is in that range. Wow. So if you got, I don't know, if you got 1 million people and Americans, right, 1 million American adults, and you took the IQ of them, 68% of all Americans, right? 68% of that million, right? 680,000 of you would have an IQ somewhere between 90 and 110. Now, since you are at college, and the average IQ of someone at college is a little bit higher than that, but roughly about 68% of you right now have probably got an IQ somewhere between 90 and 110. And I don't know any of your IQs, but I'm pretty confident that that's true. Now, if you move to 2 standard deviations from the mean, right? So 100 add 20 and 100 take away 20, you get that range, right? Which is what? From 80 to 120. And in that range, 95% of all the data will lie. Right? So 95% of Americans have an IQ between 80 and 120. Right? 95% of you in this class will have an IQ somewhere between 80 and 120. And then you get one more. If you go 3 standard deviations, that's from there to there, right? So there to there, which I'm going to have to do down here. So that's from 70 to 130. If you go from there to there, you get 99.7% of all the data. So I can be pretty confident that virtually every single person, right, 99.7% is almost everybody, right, has an IQ somewhere between, in this case, 70 and 130. Now, it's not 100%, because isn't there a little 0.3% left over? But isn't that for the outliers? So who would an outlier be? Somebody whose IQ was less than 70 would be an outlier, right? And somebody whose IQ was bigger than 130, right? At the 130 plus, that's over here. That's where Scottish people are. And over here at 65, that's where American football players are. Oh, come on, that was a good insult. American football players, Scottish people. That's totally untrue. Are we good so far? Do you see why this rule, 68, 95, 99.7% rule, is a much better rule to tell you what the heck's going on? Right? 1 standard deviation, 68% of data, plus or minus 2 standard deviations, 95, and plus or minus 3 standard deviations is 99.7. So far, so good. Right. Now, you can also use this for other things. Here's one very simple example. The range of data, right? From the smallest IQ to the biggest IQ, right? And that's going to vary because sometimes you get outliers and so on. But the range is typically 6 standard deviations. So if I collected a big sample of Americans and I found out what your IQs were, the range, right, biggest, take away smallest, is approximately 6 standard deviations. It's about a range of 60. And if you look at that, isn't it the difference between here and here? You like that? See if we can use some of this thing. The mean height of Scottish people is 56 inches, and that their standard deviation is 4 inches. If I take a sample, let's call it a large sample. If I take a large sample, the range is going to be 6 standard deviations. The range is going to be 24 inches. So from the tallest person, adult, that I find to the shortest adult I find, the range between those will be approximately 24 inches. I would like to know what range of heights do you get for the middle 68%? What range of heights for the middle 95%? And what range of heights for the middle 99.7% is? And I'm going to draw a little picture to help answer that. Heights are normally distributed. They look like that. The mean is 56, so it belongs here. The standard deviation is 4. So you go add 4, add 4, add 4. And you go take away 4, take away 4, take away 4. And by the way, that is not the average height of Scots people. They're much taller than that. But since I'm small, I wanted to look big. Right? So, but it's the data, it's correct. Right. Now, you want to know what range of heights. Now, when I use the word range of heights, I don't mean the word range. I know it's the same word. I just mean from the smallest to the biggest, right? So if I wanted to know what would the range of heights for the middle 68, wouldn't it be 52 to 60? Are you happy with how I figured that out? That in 52 to 60 inches, that's where the middle 68% of all Scots people would lie. If you wanted the middle 95, you start at the mean, right? And you go 2 standard deviations either side, and that takes you to here, to here. So that one is the 68%. This one is the 95%. And that would be from 48 to 64. And if you want to know what the middle 99%, which is almost everybody, you would go 3 standard deviations. That's from there to there. And that would get you 99.7%. And that would be from 44 to 68. And I could also ask you questions. So that might be question A, and this might be question B in 3 parts. And question C might be, is a person in Scotland who's 72 inches tall an outlier? And is somebody who's 45 inches tall in Scotland, are they an outlier? Well, you can also tell from this picture. Outliers are numbers which are extremely big. The rule for extremely big is you should be the mean plus 3 standard deviations or bigger, which means shouldn't you live here, right? All the numbers over here, or 3 standard deviations and smaller, shouldn't you live here? So these are where the outliers live. So that test that we did yesterday, can't we just use this picture to do the same test, right? Because isn't that 68 the mean plus 3 standard deviations? And isn't that the mean take away 3 standard deviations? So let's answer the question. Is 72 an outlier? Is 72 in this shaded area? Is 72? Yeah. So your answer would be yes. Is 45, is somebody who's 45 inches tall, is that an outlier?
No.
No. isn't this quite useful? That if all I know about my data is that it's symmetric, and I know the mean and standard deviation, can't I tell you all sorts of things about it? Like, this is an outlier, that's not an outlier. This is what the range would be, roughly. And can't even tell you, right, the middle 6 to 8% of whatever it is you're measuring is between, in this case, 52 to 60. I can tell you this is an outlier or that is an outlier. All of that is contained essentially inside this diagram, isn't it? Called the empirical rule, or as I prefer, the 6 to 8, 95, 99.7 rule. Any questions about that? Are we good?
I have a question really quick.
Yes.
Where does the 6 come from when we're talking about the range? It says 6 times the standard.
Why is it 6 and not 4 times or 10 times, that kind of thing? Yeah, okay, let's show you. If you go in the mean, that's 1, 2, 3 standard deviations. And if you go from the mean, that's 1, 2, 3 standard deviations. And if you think about that's probably going to be your smallest number, and that's probably going to be your biggest number, especially if you don't have outliers, which is what we're hoping you don't have. Won't the difference between here and here be 6 standard deviations worth?
Yes, okay, that makes sense.
That's where it comes from.
Sorry, what happens if there's more than 6 standard deviations, like when you draw?
Well, you could keep going forever, right? You could do 4 from the mean, 5 from the mean, 6. We don't do that because we don't have, well, we could, but we don't choose to do it because that's a good stopping point. Would you agree 99.7s, pretty much everybody? There's not a lot of benefit. If you went to 4 standard deviations, I don't know what the number is, but I'll make it up. 99.93% of the data is in that range, right? Or some, you know, whatever that value is. So we typically stop at 3. 3 is a good number because isn't that also where you stop if you're looking for outliers? Right?
Yes.
So the two things kind of come together nicely if you stop at 3 standard deviations.
Thank you.
Good question. Anything else? Any other questions? Anyone? Right. I'm going to show you some of the homework because that's, to me, I think it's important to just see how WebAssign asks us the same type of things that we've been covering. And I think it's on this page. Are you looking at question 1? Right. Now, there are some questions here where you're going to get the mean and standard deviation, pardon me, of quite small numbers. You see them? There's only like 5 numbers in each. When you don't have the salt button, aren't you going to have to use your friend TI-84? Right? But we've went through that yesterday. Remember all the buttons that you press to get the data in, and then you read off the answer. So they are doable. But sometimes, just sometimes, you can do at least half the question without a calculator. So I'm going to pick a really silly one, but I like it because it's silly. And I'm going to tell you the answer without a calculator. And it's question B. What is the mean of those 5 numbers?
23.
Yeah. Would you agree I don't need to do it in the calculator, right? Silly question. Of course it's 23, right? There's none else it could be. What's less obvious is I can tell you the standard deviation. Now, the standard deviation is a number that tells you how spread out the data is, right? And it's always positive. So what do you think the standard deviation for those numbers would be?
0.
And you would be right. Now, that guy and that guy, nah, you're going to have to use the calculator, right? I could have a good guess at the mean for that one. Does anybody want to tell me what the mean of those 5 numbers are without adding them all up and divided by 5? Because I'm pretty sure I know what the mean is. What is
23.
it? Do you agree, Cody, 23? Sydney says it? Yeah. Would you also agree that you couldn't really do it for that number? That's C. right? And those numbers just all over the place. Wouldn't you have to do it the old-fashioned way, right? Add them and divide by 5. Are we good with that? Some more questions. These ones are nice small data sets, which thankfully that's good, but aren't you going to have to do them in your calculator? Right, there's no shortcuts.
Yeah, so I got a
Yes.
question for that one. So I missed the explanation on how to do it on a calculator, and I got a different calculator, and I can't figure it out. So I had to do it on the paper, right? Find the square root, and then
The deviation squared, all
Do
divided
it.
by n minus 1, that thing.
yeah, then square it.
Oh God, you
Plus
poor
square.
soul. Go and
But for
contact.
the 5, it's 5 minus 1.
Yeah.
For the mean, but for the 4, I did the same thing, but I kept getting it wrong because
Right, so it's 4 minus 1, which is 3, Cody.
yeah, that's what I was doing, but it was wrong.
Right. Wrong is a vague word in these
Incorrect.
kind of things. You might have said 3.24 and they might have said 3.27. So you got to look at the rounding off. Now, in the question that you're talking about, they say round off to see that 3 decimal places.
Correct.
Here's a thing that you have to be careful about when they say that. Don't do all your in-between calculations to 3 decimal places. Do
Yeah.
all the in-between calculations to 4 or 5 decimal places, right? Including the dividing and the square rooting and all that. And the only time that you go down to 3 decimal places is when you're finished. So you get the answer 1.2345. It's then that you round off. And you might say, well, surely that's not going to make a lot of difference. Unfortunately, it can. If you round off all your in-between calculations, like that decimal to 3 decimal places, and then this square root of 3, and then this, if you do it all over the place, the final answer and the one you would have got if you'd done more accurate calculations can differ by a significant amount. So you put in 1.4, but if you'd done it the other way, it should have been 1.5, right? And that's a good chance that's the most likely reason you got that wrong. I'm trying to save you a lot of grief here, because if you're doing it the way I think you're doing it, it is horrendously boring and horrendously long. Will you
Can I
back
just
me
do
up
it
on
over
that?
the calculator one more time?
So I'm going to show you again on the TI-84. I also would ask you to strongly figure out a way of getting a TI-84. Some of my students have said you can get an app on your phone now that does the TI-84. I've got one person nodding, so I'm picking Isabella. Isabella, are you nodding because you know that's true? Is that the thing you've got? Is that the app or the TI-84? What have you got?
Yeah, it's the app for it.
It looks just like it. That is so cool. Right, so Isabella knows where the app is and she will send Cody a link. Is it, can you do it in an Android or what's the other one?
So. I think it's a universal app.
Right.
So what is it?
So,
TIA4?
right. So what do you search for? TI-84 emulator, probably, something like that?
I just searched up statistics calculator and the calculate 84 came up.
Got that? So that's, if you don't have a TI-84, a physical one, that would be a workaround. If you if you email Cheryl Phillips, I'll put her email down for you. You can get a loaner from the college, right? So if you give me a minute, I'll write her.
Well, they sent me a statistics calculator, but it's a Casio FX 300ES.
I don't know how to use it. I wouldn't be any good to you. And especially the fact that we're not physically here makes it even worse. So. Right, she's Cheryl. And the reason you shouldn't phone her is that poor woman is like inundated with phone calls. And so emails are easier. So if you contact Cheryl Phillips at olympic.edu and just say, I'm in Mr. Robertson's statistics class. I've been told I can get a loaner of a TI-84 calculator. And she will say, yeah, we've still got one. Come in Tuesday and I'll give it to you, or whatever.
How much are they to purchase personally? Like,
if you want to buy one, I think the going rate, somebody might tell me, I think it's about $105 brand new. So exactly, that's not cheap. You could find a little brother, beat him up and steal it, but I'm not allowed to tell you to do that. You could find someone else's little brother and steal it, but I'm sure I definitely am not allowed to tell you that. You could get it secondhand. You know, that's kind of hit and miss. Don't you get stuff secondhand, you know, eBay or whatever, and it's good, and then you get stuff and it's broke, right? I'm not sure about that. Goodwill. Some of my students have said they've went to Goodwill and found one.
I did find an app for Android that says it's the TI 84 calc.
Right, so Cheyenne, if you got a link to that, or just
I'll type what it's called in the chat for everyone.
okay, so if anybody's interested in the one Cheyenne is, have a look at the chat. While she's doing that, I'll get myself kind of organized. We kind of, as you can see today, it really does matter, doesn't it? You got to have something like a calculator, because salt isn't always going to be a choice. Okay, now I'll return back to the screen, and you can, those who are interested can get that one. Here is yet another one. Here is 8 people's blood pressures, and you're going to get the mean and the standard deviation. Right, now I'm going to go through it on my calculator with that set of data, so that if you've got a TI-84 or you're eventually going to get one, you can watch this video again and just pause on it. I'll take you through the steps. So, first thing you do is you hit Start button. And you pick option 1, which is edit. And you press enter. So, start button, it's already in option 1, press enter. You're then going to have a guy that looks like this. If there's numbers as it are here from a previous question, hit delete to make those numbers go away. Right, because you need a screen like that. Okay. And then what you do is you type in your data. In my case, you type in 113, enter. 121, enter. 130, enter. 153, enter. 129, enter. 117, enter. 101, enter. And 120, enter. Right? So you type in all the data. Remember, you know, kind of obvious, you have to hit enter each time. So far, so good, right? Type in your data. Step 3, can anybody remember what button I press again?
The stats button.
Yeah, button.
Yeah, start button it is. So press the start button again. But this time, you're going to move to the calc menu. There we go. And then you're going to choose option 1, 1 var stats, right, which is set up for, right? It's highlighted, number 1, 1 var stats. And you're going to hit enter. And you should be looking at a guy that looks like this. Now, if you've got a more modern machine, it might look a little different, but it's essentially the same thing. All I need to do now is, see that little flashing thing there, that guy there? I need to put L1 in there. Can you remember the 2 buttons that I need to press to get L1?
Second and then 1.
So you hit the second button, which is that guy, and the number 1 button. There it is. And of course, press enter. And you will get all sorts of things. In fact, isn't this the same place you get the 5-figure summary if you want to do box plots? And this is the same place where you'll get all the other things. So what we are interested in right now is that number, which in this case is 123, and that is the mean. And the other number that we're interested in looks like that. In this case, it's roughly 15.2. Or if it's 3 decimal places, I guess it's 15.203. It depends on what the WebAssign says they want the answer to, right? And that's the guy that we are going to call the standard deviation. Now there's another guy underneath it. It's 14.221. Do you see that guy? You are never going to use that guy as your standard deviation unless you get the question and it specifically says the population standard deviation. So if it sticks the word population in the front of standard deviation, then you would use that. I don't know of any homework question that asks you that, so you're not probably ever going to see it, right? But just in case in the future you're looking for a population standard deviation, you would use the second number. Technically speaking, that guy there is called a sample standard deviation. But almost universally, that's what you tend to work with, right? You tend to work with samples, right? You don't know everybody, right? You measure some, but not everybody. And that's a sample when you do them. Are you comfortable about the steps then that we would use to get that answer? Okay. And you can pause it and go back to this piece of the video if there's something that you might have missed. So I've got some things in the chat. Someone, Maggie's mentioned that you can actually rent a calculator. Maggie, do you know how much it costs? No.
I don't. I saw an ad for it the other day, though. That's why it jogged my memory.
Okay, so if you want a physical calculator, some people like, just the touch of a physical calculator. Android Play Store has one. Right, they're all in the chat. So if you hit the chat button, you can get more details. Right, I'm now returning back to our homework and let's look at question 3. And they told us the mean and it was 123. And we figured out the what that guy, and they want the answer rounded to 3 decimal places. So here goes. So 15.203. And then they hit you with this guy called the variance. And the variance is very often called S squared, which kind of gives you an idea what you're going to do to calculate it. And what you're going to do is take the standard deviation and square it. So the variance is just another measurement of how spread out data is. It's not as used as often, but it does get used sometimes. So standard deviation and variance are very closely connected. Isn't the variance just the standard deviation squared? That's all it is. So I've got 15.203, which I'm now going to square. And the answer that I get is to 3 decimal places, because that's what they asked all of the answers to be, 231.131. That's what it is to 3 decimal places. So if I gave you a set of data right now, are you comfortable about finding its mean, its standard deviation, and now and again, but not that often, its variance? You feel yep, I can do the calculator. I know the buttons to press. I can get those guys. Right. So here is a slightly different kind of question. Write a set of 8 numbers that has a mean of 70 and a standard deviation of 0. That is not as hard as it looks. What would that data set look like? 8 numbers, mean is 70, standard deviation is 0.
Wouldn't they all be 70?
Yep, and isn't that a silly question? 70, 70. So when they ask you and they use this phrase, comma separated list, you would go 70, 70, 70 on board, right? You just do it until you've done 8 of them, right? If you do 7 of them, it'll tell you you're wrong. If you forget to put the commas in, it will tell you you are wrong, right? So it's very pernickety, right? So when it says a comma separated list, put them all in. Don't get lazy like me and say, I don't want to write the other 5, right? Because it'll make you wrong. Now, the next piece of that question is quite cool. It says, is there more than one possible set of numbers that this would be true? In other words, can you find another example where the mean is 70 and the standard deviation is 0? Do you think it's possible to have another set of numbers where that was true? What do you think? The mean has to be 70, but the standard deviation has to be 0. Is there another combination that could happen? What's your gut feeling? I could tell you, but come on.
There could be any other number other than 70 for the standard deviation 0, right?
Correct. So it's the first thought. It ain't possible, right? There's only one way that that's going to happen, right? Now, if I went and said to you 8 numbers whose mean was 70 and whose standard deviation was 10, couldn't there be lots of different ways that could happen? Of course, I wouldn't be able to, off the top of my head, give you an example of that because it's quite hard to make a data set have a standard deviation of 10. Would you agree that's something, hit and miss whether you could figure that out? Now, this question is beginning with our 68, 95, 99.7 rule. And you notice that the way they're going to phrase it is not visual, but although I would probably do it as a little sketch, but we should be able to figure it out. The typical amount of sleep per night of a college student is bell-shaped, and the mean is 7.4, and the standard deviation is 1.8. So can you imagine me drawing that big hill? Wouldn't right in the middle be 7.4? Okay, to get the 68%, wouldn't that be starting at the mean, go 1 to the left and 1 to the right? Okay, so starting at 7.4 and take away 1 standard deviation, which is 1.8. And then on the big side, the mean, add 1 standard deviation.
The mean is 7.4.
Did you all catch that deliberate mistake? Does anybody even believe that's a deliberate mistake? Because it was just a mistake, right? And I do that frequently. Now, I'm not going to put what they're equal to, because couldn't you do that yourself? What would I need to do the 95% one now? Because we kind of started today with that. I'd start with a mean of 7.4, right? But if I wanted 98% or 95%, I should say, right? What would I do?
Add or subtract twice of the standard deviation.
Right. Now I'm going to do the subtraction in my head. So if the standard deviation is 1.8, if you add and subtract 2 of them, then you would take that guy, right? Whoa, what's that? That was weird. Huh. Looks like I picked up some code from somewhere. Just putting these guys in as placeholders. There we go. Add. And add 2 standard deviations. And over here, take away 2 standard deviations. And wouldn't that be the range of values where 95% of college students sleep, right? Let's do 99.7. Well, won't that simply just be the mean take away 3 standard deviations? And the mean plus 3 standard deviations. So I'll put it in as a calculation this time. Right. Okay, let's actually do that calculation. 99.7% of college students typically sleep, let's say 7.4, take away 3 times 1.8, and that ends up being 2 hours. Wow. And on the other side, it's 7.4, add 3 times 1.8, and that ends up being 12.8. Let's take the calculations out the way because they're a distraction now. That's quite a big range, isn't it? But does it seem reasonable that almost every student sleeps somewhere between 2 and 12 hours typically? Now, some students miss a night's sleep because they've got a big project to do and it has to be done, right? But in a typical, you know, Thursday where nothing specific is happening, that would get that. I would be very worried at that student there or somebody who slept less, and because they have got serious insomnia.
That or they're in the military.
Well, yeah, even the military, they don't do it all the time, right? They do get normal sleep most of the time. And this one here, I'd be really worried about them because you might have a little brother who's like this, especially when they're teenagers. Don't they just get up at 2 p.m.? You know, they went to bed at midnight or something, whatever, right? That student there, or those students in that extreme, would be considered unusually long sleepers, right? And so that might be a medical issue, and there are people who have medical issues with that. Now, we have time for me to do this next one really quickly. So while I'm getting set up, why don't you put your last name down for attendance? And I'm setting up that 68, 95, 99.7 row. Okay. I'm going to show you how this rule gets used in a practical sense. Let's take medicine, right? So some of you are going to be in the nursing program or whatever. And one of the things that you'll know that if you get blood work done is that they'll tell you what the thing is, right? You got 14.5 calcium level, whatever it is, right? They have numbers associated to them. And then they very often tell you if it's high or if it's low or if it's dangerously high, right? Those kind of key markers. So I'm making the number up because I don't know it, but let's suppose you measured someone's potassium level, right? And the average for the general population is 30, right? Adult population. And for the standard deviation, it's 5. So you imagine that data is something they've collected over time, right? They've got a lot of data on potassium levels for adults. And so there's the mean, right? If you do one standard deviation, that in this case is 25 to 35, wouldn't we call that the normal range? We would say, yep, none to see here, your potassium level's exactly where it should be, don't worry about it. Great, that would be normal. Now, if you go 2 standard deviations, you get to 20 to 40. In this region here, isn't that a bit in the high side? So you would say, if you have a potassium level 35 to 40, you would call that high, right? Your potassium level is high. Now, it might not be, you know, we need to rush it into, you know, the hospital and emergency treatment, right? It just means it's high, you know, we'll keep an eye on it, right? But isn't this side here a little bit on the low side? So that would be from 20 to 25, and we would call that low. Again, we wouldn't necessarily do any treatment, but we'd be keeping an eye out, right? Now, if we move to the last one, which is here to here, right? And if I stop here and I stop here, these two regions, they're very interesting. So let's take the 40. Well, actually, I could just say 40 plus, wouldn't I? I don't care. After 45, it's just as bad, isn't it? So I'm going to call that 40 plus, right? Now, isn't that extremely high? Isn't that something the doctor would say, yeah, your potassium level's not good. I want you to come in. I want to do some more tests. Maybe your pituitary gland's not working, or your thyroid's, whatever it is that makes potassium go high, right? I want to come in and have a look at it, right? Because at that range there, aren't you in the very high, unusual level for normal people with normal health to have a potassium level up there? And at this end here, which is basically anything, right, less than 20, right? That would count as extremely low. And for the same reason, wouldn't you probably get the phone call, yep, you need to come in. I don't like your potassium level. Let's figure out, do some more tests, see what it is. Sometimes it's very simple. In this area for here, and I can tell you for true in Scotland, we're much further north than you. And what that means is that in Scotland, low vitamin D levels is very prevalent because we are not getting the same amount of sunshine, right? Our winters are longer, we don't get a lot of light, and vitamin D very often gets produced through your body in light unless you eat vitamins. So it's almost guaranteed that somebody in Scotland, if they don't take vitamin D, ends up having a really low vitamin D level. It's not